All right. Can you hear me okay in the back? Cool. Just waiting for the cutover. Perfect. Thank you. How are you doing? All well? Cool. So a little bit about my background. I am a developer advocate at Red Hat, as already mentioned. Before that, I was at Mesosphere, so doing containers for around 4 years now. Before that, I was at MapR, being a data engineer there. And before that, I did research. Nowadays, I'm mainly developing in Go, but a lot of things, including Java. I was young and needed the money, and kind of like turned off. So I started out as a developer, but over the last 4 to 5 years, more and more went into this operational domain. A little bit about yourself, so I know to who I speak to. Who is an admin? Okay. Site reliability engineer. Okay. Developer. Okay. Majority. QA, quality assurance. We don't do that. Cool. Architect. Okay. Product or project manager. Ish. Pointy hairy boss. Nope. Okay. All right, we are amongst ourselves. That's great. So let's have a look at the Cloud Native Lifecycle from the basics. If you look at what the Cloud Native Compute Foundation, the CNCF, regularly updates there from low-level infrastructure stuff over provisioning, container runtime, service mesh level things. You see there are a lot of different projects, and some of them are actually have their home in CNCF. In terms of terminology, we typically talk about the containerized setup, so everything from building a container image to running it in a container orchestrator like Kubernetes nowadays, typically the standard there. We're going to talk a little bit about observability, and that includes monitoring, logging, tracing, and so on. We typically talk and assume loose coupling between the components, so the containers and microservices in there. And let's keep in mind that delivery and deployment is not the same, right? Delivery just means you're able to deliver a certain artifact at a certain point in time. Deployment actually means rolling it out, for example, in Kubernetes as a container. The actual starting point of Cloud Native really are the 12-factor apps. Who has heard about that already? Okay, so half of you. Started out a couple of years ago in the context of Heroku, and they essentially documented their best practices. And if you look through that, you can look at it 12factor.net if you want to. Most of it, if not all, you will find in a Cloud Native environment. On top of that, you also have things that the Heroku folks obviously were not that worried about, and that is portability. So you want to avoid platform lock-in, and Kubernetes gives you exactly that. Also, that means that you can run stuff both on your local or on premises and in the cloud. And typically, the unit of deployment moved from virtual machines to more and more containers to nowadays even functions. I'm going to talk about that at the end as well a bit. We are dealing with distributed systems, so we're assuming a horizontal scale out on commodity hardware. We have to still acknowledge the fallacies of distributed computing, and typically stateful services. So most of the stuff I'm talking about is stateless, but if we're talking about stateful services and they're inherently cloud native, then they know how to shard their data across a cluster. There are a couple of roles we're dealing with, and this is a bit more specific to Kubernetes. We have cluster admins, we have namespace admins, we have the developers, and we have users. We're going to focus on the first three for now. A cluster admin typically does things like provision infrastructure. That depends if you're in the public cloud or on premises. So you would, create a VPC or VMs and whatnot. You would also take care of infrastructure monitoring, installing and upgrading the platform. That again depends on if you're using managed service or not. You would also deal with user management. You might have LDAP there, whatever, and bring that into the platform. In the context of container images, you're typically also responsible for managing the base images. So depending on the programming language environment, you define, here's a Node.js, here's a Java, here's a whatever base image that then the developers take and create the application container image for that. and you typically also define quotas, typically on a per namespace level. Namespace admins, again, namespace being a community-specific term, but you typically have some unit there. You're typically taking care of the application lifecycle management. That might be your own bespoke developed applications or off-the-shelf components, but you're essentially taking care of installing them, upgrading them. Managing also the monitoring there on the namespace level and on the application level. If not already set or defined by the cluster admin, you probably also take care of quotas. And one big thing to take care of in context of security is role-based access control, which is front and center in Kubernetes at least. As a developer, your main activity in terms of artifacts is essentially creating application container images. Obviously, the testing integration bits. Troubleshooting, there is an interesting aspect. Who is going to be on call? Less and less the application, the admins, but more and more developers, especially if you have many microservices, and that even gets more dramatic if you're in a function as a service or serverless environment. And last but not least, the application level monitoring as well, or tracing as well. We're going to talk about that a bit. A couple of challenges there. First and foremost, and that is where DevOps actually came from, aligning the incentives. If you think about that, operation folks focus on keeping stuff stable, right? As long as it's stable, as long as everything stays the same, you have a great running environment. Developers are incentivized by bringing new features into the game. And that seems like something that contradicts. In the context of cloud native, we find that we can bring these two apparently opposing streams together. And that has partly to do with the fact that developers take care of things that would traditionally have been taken care of by operation folks, such as monitoring. We discussed already the fallacies of distributed computing, and that is something that I quite often see when being on-site with customers is a little bit neglected. Microservices, seem to be very powerful and very, fashionable, but people underestimate the fact that this actually means that different microservices, different containers run on different nodes, and the network will fail at some point in time. And one bit that is also sometimes overlooked or sometimes considered as an after effect is security. And luckily, Kubernetes provides you with all the things. You just need to make sure that you don't rely on the defaults in a nutshell. So let's have a look at how we actually go about building and delivering apps on Kubernetes. If you look at what you would currently more or less do, you have the build artifact, so your code, configuration, and credentials. And that is already one thing from 12 factors, that you don't have the configurations and credentials in the code, but you have that separate artifacts. You have a CI/CD pipeline that takes the stuff from the code repo and produces some artifact, binary or WAR file or whatever, and deploys that on, for example, a VM. In the cloud-native way, we still have code configuration and credentials, but now we have other artifacts as well to take care of. For example, the container image manifest that defines how a certain container looks like, the container runtime manifest that essentially explains or describes the deployment of that container. And if you're using a service mesh, I'm going to talk about that later a little bit, you also have a manifest there. You still have your code repository where you have all the artifacts in there and the CI/CD pipeline. And now you have a new component, a container registry, that serves a little bit as a tool that both on the development side and on the operation side are involved with. And at the end of the day, you have a container image in the container registry, and the container runtime, container orchestrator then pulls that from the registry and deploys that, runs that, potentially using service mesh as well. Conceptually, from a developer point of view, you have a couple of modes available. You can have something like this, set up pure offline where both the development environment and the cluster runs locally. And I'm going to show in the demo one of those, which is Minikube, a standard tool in the Kubernetes ecosystem. You can have a proxied mode where you have a live cluster running somewhere and you're proxying parts of the services to your local machine or the other way around. And you can imagine in a microservices setup where you have multiple dependencies, this is necessary. You can have a live setup, and I'm going to show that as well in the demo, where you're essentially having a cluster somewhere and developing locally, and for example, having a webhook triggering a build in that setup. And you can have pure online environments. AWS has that, and Eclipse CJ is also something like that, where you have both the development environment and the cluster essentially in the cloud. So essentially all you have is a browser on your laptop. If you think about how we deployed Monolith, you had essentially a version 1, and at some point, weeks or months later, you had a version 2. Now, if you break up that monolith in, it's typically not 3, it's many, 50, 100, 200. You might start at the same time with version 1, but then different teams are looking after different microservices, and that means that at any given point in time, you might have any given version there. And that has a few implications. That means that that comes back to the loose coupling. You cannot simply assume one place if you're debugging, troubleshooting, or profiling. So you need to have a setup, and that is typically done through distributed tracing that allows you to follow the path of a request through all the microservices. And this, as you can imagine, already poses a challenge, but luckily the tools we're going to talk about in the next part solve most of that. So let's have a look at the tooling, and I'm going to have an approach where I'm going to talk about a lot of tools. If you're interested in any particular one, I'm around later on, we can have a discussion about that. It's really just there are many tools, and depending on your environment, your preferences, you might want to pick the one over the other. The one tool that is kind of like the standard for container orchestration, container lifecycle management is Kubernetes. And that mainly means you have to make a decision there if you're going to roll your own Kubernetes distribution or use one of the over 30 certified distributions out there. At the end of the day, you have a very extensible modular API, and most of these components are nowadays standardized, so you have interfaces, de facto standards for pretty much everything, for networking, storage, and so on and so forth. In terms of developing, I talked early on about the modes in general. There are many tools. And again, depending on your environment, you might want to pick the one over the other. Also depends on in which phase you are. For certain phases, if you're alone and doing some experimental work, trying out something, some things might be better than others. If you're in a team and multiple microservices are involved, you might choose others. I have one article at the end that Ilya from Reflex myself just published 2 weeks ago on Kubernetes blog that goes through that and discusses that a little bit with pros and cons if you want to have a look. Just to give you an idea, there are a lot of projects out there that allow you to do iterative development with Kubernetes, essentially. So we were talking about extensibility. As I said, the simplest way to extend Kubernetes is our hooks, and that are provided from the pod level, things like pre-start or whatever, to the API server, where you have webhooks that you can call out to change the flow there. If you want to be a bit more advanced, you can write an operator, which is a fancy term for a custom resource definition, a custom controller, and the custom resource is essentially extending the resources that Kubernetes already has built in, such as pods, services, and so on. And a controller is essentially just a control loop that reacts to certain events there, typically on this custom resource. And there's this operator framework recently released that helps you bootstrapping that. And if you even want to go a step further, you can develop Kubernetes native apps using libraries like Client Go. One big part, and that is again something that application developers and admins, namespace admins or cluster admins do together, essentially are container images, and you need two things for that. And that is on the one hand a pipeline. There are a couple of generations there, the traditional ones and more cloud native ones, if you want, that are able to take your artifacts, as discussed earlier on, code and so on, and build the container images for you, and then put them into a registry. And there again, depending where you are, if you're in a public cloud environment, each of the big providers, Azure and AWS and Google, have their own built-in registries. Or if you want to stay a little bit more, have more control over that, or if you run on premises, then things like Artifactory or Quay are great things to use there. But in any case, having a registry there that is able to serve these images in a high performance fashion is really important for the overall flow. One big part in this microservice, containerized microservices setup is observability. And that includes monitoring, both on the infrastructure level and application level, logging, the same here, distributed tracing, and let's have a look at that. So in monitoring, you're essentially talking about the node itself. Typically, as I said, the cluster or namespace admin, container, and the application level. All of these metrics go through an event router, which nowadays typically is Prometheus. And then you have different downstream things where you can, for example, plot them on a dashboard, having alerts on that, or put them into some kind of long-term storage for different purposes. Logging, pretty much the same setup. Host and intra-host logging is typically mainly for infrastructure admins interesting, and container runtime and service or app level mainly for application developers. Distributed tracing, there is a standard for that. It's open tracing, and initially essentially came from people trying to do that kind of thing through time synchronized logs, so trying to align these timestamps, and that's one of the impacts of that you have different nodes there, that the time stamps themselves are typically not reliable enough that you can use them. So essentially what you're doing with distributed tracing, whenever a request comes in, you assign that an ID, and that is carried through all the microservices, and with that you can build up a trace with that. Two tools there that nowadays are widely used are Zipkin and Jaeger, and again, there the question is, do you use them standalone, or if you have a service mesh like Istio in that setup, they typically bring that from themselves. A couple of good practices, which is specific to Kubernetes, to be fair, is using namespaces. They are kind of a way to carve up a cluster in different smaller portions, and then you can outsource the management of these namespaces to a certain person. Using service accounts, there is a default service account as there is a default namespace, but having this identity per application is a great way to isolate things and also a necessary precondition for RBAC. There are a couple of policies built in, and service meshes allow you to do even more. Pod security policies, for example, you can say you can drop certain capabilities, or say don't run that container as root. With networking policies, you can define how certain services within the namespaces can communicate with each other. One thing that sometimes is forgotten is setting resource requests and limits, so essentially defining how much CPU and memory a certain container may consume. If you don't have that, then you essentially don't have any guarantees in terms of which one of the containers will be killed if there is not enough resources available on a node. And also in terms of the overall lifecycle, liveness and readiness probes are essential. Different components, so liveness probes are used by a component that sits on each node, the kubelet, to determine if a container is still considered live. And the readiness probes are mainly used for deciding if certain pods or containers in these pods should be routed traffic to or not. That's used by the service resource. And one last thing here, kubectl apply is essentially a very nice way or canonical way to change the state there rather than just creating something there. I'm going to show you now a demo that does essentially the same thing twice, once from the perspective of a namespace operator and once from the perspective of a developer. And to do that, I put together a very simple cloud-native app consisting of 2 microservices in the stock domain, if you want, the stock generator written in Go and the stock consumer written in Node.js. It's up there on GitHub if you want to try it out yourself. The stock generator on a certain port, on a certain path, generates this JSON, essentially per symbol a certain value, random generated, and then the stock consumer takes that data and creates a moving average out of that. Very, very simple. So let's move over to this. Can you see that in the back? Is that okay? Cool. And of course, I have prepared a cheat sheet here. So the first thing we're going to do, as I said, best practice, always create a namespace. I'm not going to create service accounts here, just the namespace. Down here, I have a watch that essentially looks at that namespace and lists deployments, pods, and services. So there should be nothing there yet. And as a namespace operator, I do things like that. For example, a kubectl apply. In this case, it's already everything pre-filled. Typically, in a more realistic setup, you would have things like Helm or any other templating language that would allow you to provide certain values for things that might change in their resource request, environment variables, or whatever. So I'm going to deploy the first one, deployment and service coming up, and the stock con, the second part. So we see, okay, container creating. So now both of these pods that are controlled by these 2 deployments are running. Services are there, and everything is fine so far. So that's available within the cluster now. And in order to call it from outside the cluster, this is Minikube here running. I need to forward this port of the stockcon microservice, and now I can essentially call it from my local host, right? Okay, so this is the output of the stockcon for a certain symbol, the moving average. Fine. So that essentially shows you how, from a namespace operator perspective, you can take any prepackaged Kubernetes application and just deploy it in this namespace. Now we're going to switch gears, and using OpenShift, which is an enterprise Kubernetes distribution that allows us to show how a developer would use the same. I could do the same commands, but I'm using OpenShift-specific one for the workflow there. Let me quickly delete the namespace here. That's another great thing about namespaces, that as soon as I delete the namespace, all the resources within that namespace are deleted. So you would now see that these resources essentially go away after some time. There's some garbage collection going on, so that takes a little bit. So let's switch over to to OpenShift Online here. And first thing I'm going to do is log in. So you see it also here in the lower right corner, Minikube default. That's the current context I'm working on. And if I log into this OpenShift Online cluster, that should change to the context that is currently active there. Okay, so at some point in time, you would see that that changes. Okay, and now we're going to create this project here. Project in OpenShift really is just a namespace with a little bit of metadata there. And once I've created that, I should see that there as well. Okay, there's nothing there yet. Okay, watch that thing again. Cool. So now I'm first gonna deploy the stock generator using a image that I have already created somewhere else manually, and essentially just pointing to that container image that is hosted on Quay.io. And once that's done, we see there's the project or namespace, and we see the deployment kicking off there. And then we also create a service for that. And the second part, which is for us, for a developer, from a developer perspective, the probably more interesting part is creating an app for the stock consumer, essentially pointing it to the GitHub repo, telling it with the context here, look at the source code in the directory or subdirectory stock.con, and a couple of other environment variables set there. And once that is done, I should be able, so stock.con is already, the generator is already running here, that's fine. And here you see that the build kicks off. We can look into that in greater detail if you want. It's essentially first cloning the Git repo and then building the container image based on what it finds there. So it's a Node.js application. That's why it takes a Node.js base image there. And yeah, once the build is done, it will automatically deploy. Then I need to patch something, and that's purely because the default port that the service that I created there is 8080, and I'm using a different one. I'm using 9898. So that should be there now. Okay, 9898. And now I'm going to create a route, which, if you're familiar with Kubernetes, is equivalent to an ingress. And with that, I essentially have this URL here. And this URL essentially is now the public endpoint. Where do we have the average? So let's first have a look at the average here. That is there. Perfect. So I don't know if you can see it. So we have something on the public internet. So you could go to this URL and try it out yourself for now. But we are interested for this demo now in the health endpoint, which is used in the Liveness probe and Readiness probe. Oops. What did I do now? All right. So ignore the first two parts, but the message is Hello London for now. So what we're going to do is we're going to change the source code and trigger a new build here. And that means I need to actually create a build hook here. And I get that through the configuration of the stock consumer. I'm going to take that GitHub webhook and add a webhook on, of course, on this repo. Okay. And now I'm going to take a shortcut. I'm not going to clone it and do it locally here. I'm just going to go in there and do it live. I know, no risk, no fun. And change that to, let's say, thank you, London. Update service. Okay, so as soon as I commit that change, which I would typically do locally, I should see that build being kicked off. And there is the second build running with that new, same thing that we saw in the first step. It again pulls the GitHub repo, builds a new container image, puts it into the integrated container registry, and as soon as that is available, you will see a new deployment coming up here. And as soon as that pod is running and I refresh the health endpoint, I should see, thank you, London, I hope. All right, so in a nutshell, that is something that a developer could use. There are other ways, for example, if you have Node.js, PHP, Python, so anything where you have hot reload, you might want to use things like Ksync or telepresence that even allow quicker turnaround times, because here every time when you do a push, as you have seen in the build, and it doesn't matter if it's this S to I, which is built into OpenShift or Jenkins or whatever, it needs to pull the entire repo, build the container image, puts it into the registry, and the container runtime needs to pull it again into a certain node and run it. And although this whole thing didn't take too long, you can imagine if you have many iterations, you don't want to go through that all the time. You want to have essentially immediate, as soon as you save, you want to see the container updated there. Okay, that was pretty much it in terms of demo. And let's see how we're doing time-wise. We have 10 minutes or something like that. Looking good. Okay. Service meshes, as I already mentioned, they add a layer on top of Kubernetes that allows you to define the communication between different services. So you can do things like saying, services in this namespace are allowed to talk to other services in this other namespace. You get things like observability for free. There is Prometheus in there. There is Jaeger or Zipkin in there. You can have TLS between different services. You can even do a failure injection. You can say, every third call there should result in a 4-4 or whatever. Just one thing, don't necessarily start with service meshes. So if you have a handful of microservices, maybe a couple of namespaces, that is really a great way to rather than doing it on your own, to get control of all these things. The most important bit, any kind of service mesh, not only Istio, there's also Linkerd and Conduit from Buoyant. Essentially, it means that rather than implementing all of these things, traffic management, and so on and so forth, in the code, in your language, you essentially outsource that to a sidecar. In Istio's case, it's Envoy, which means for yourself or as a developer, there are no application changes. Everything is injected at runtime. Data meshes, somehow familiar or somehow related to service meshes, they essentially do more or less the same thing for the data that you have. And currently the only real example there is .mesh. It's a UK-based company, essentially allowing you to take snapshots or versioning of data sets that you have there. And you can use that for a couple of things. I'm personally using it in the context of machine learning and data science. If you're familiar with, for example, S3 versioning, then you probably know already what it is. So you want to make sure that at any point in time, if you have a database running there, you're able to say, okay, take the current state of that database, and then you can, for example, use that to debug it or to recreate things or whatever. Essentially, this snapshotting of data. Last but not least, a thing that in the last couple of years really became a big thing, and that is serverless or function as a service. Essentially what you have there in an event-driven environment, you have certain triggers. That could be things like uploading a file to an S3 bucket or whatever. Time could also be a trigger, so every 5 minutes or whatever. As a developer, you essentially only upload your piece, your function, that is stateless and typically limited in how much time it can consume, runtime it can consume. And then you have CLI or UI where you can upload it and define certain triggers. And then you have integrations because this function is stateless, so you need some data store to externalize the state there. And just to give you an idea how we're looking in terms of landscape in the Kubernetes setup, outside there, essentially, if you're running in a public cloud, AWS Lambda is pretty much the 500-pound gorilla. It has some 70% of the market share there. But if you're running on Kubernetes, here are a couple of things that you can use. And as you can see from the last column, most of them are still early days. And yeah, if you want to know more about that, happy to talk about that. At the end, I've put together a couple of resources, books here that you might want to go through from more conceptual side to a more hands-on side. and a couple of articles that cover a lot of these things in greater details.